Hello and welcome everybody to Calculus. Today we're talking about section 2.2, basic differentiation rules and rates of change. So all throughout today we're going to be taking that limit definition of the derivative that we learned last section, and we're going to apply it to a couple situations to come up with some basic rules that are going to make our life easier. So just bear with me as we discover some of these rules, and then we're going to learn how to apply them. So the first one we want to look at is the derivative of a constant function. So it says let c be a constant and let f of x equal c. So here it just equals some number. And it says use the limit definition to find f prime of x. So all we have to do here to use the limit definition to find f prime of x is just start with our limit as delta x goes to 0. And let's rewrite our difference quotient. So this is good review for us. Okay, again, that needs to be memorized there. And if f of x equals c, all we have to do is plug c into our equation for x. Now when we think about f of x plus delta x, if f of x always equals c, then this is going to equal c as well. And f of x equals c, and then here we have delta x. And before we go any further here, we know c minus c is 0. So the limit delta x approaches 0 of 0 over delta x. So as delta x gets closer and closer to 0, this number is also going to be getting closer to 0. Now another way we can think about it, what does the graph of a constant function look like? Well, it's a horizontal line. And we know that the derivative is the same thing as slope. So what's the slope of our horizontal line? Well, it's 0. So the derivative of any constant function, c, is going to be 0. And that is our constant rule. And here you can see it more formal. If c is a real number, then the derivative with respect to x of c is 0. So let's look at our example. It says find the derivative of each function, y equals 7. Well, y prime, 0. How about this one? F of x equals 0. Is 0 a constant? Yes, it is. And so f prime of x is going to equal 0. In letter C, we have s of t equals -3. So using our derivative notation, s prime of t equals 0. Now this next one looks a little bit funny. It's 4 pi squared. Well, pi is a constant, so pi squared is a constant, and times 4 is still a constant. So for letter D, y prime still equals 0. Got it? Pretty simple. Our next one is the power rule, and this is going to be one of the absolute most important rules that you're going to learn in this semester. So we're going to do a little exploration here of how we can determine the derivative of any x to the nth power. So we're just going to start by expanding these binomials, x plus delta x squared, and you'll see the x plus delta x in our difference quotient, and so this is going to be helping us as we define this. So any binomial squared takes on this form. Then we want to do x plus delta x cubed, and we've dealt with this a little bit. Remember, we used Pascal's triangle for our coefficients. So 1, 3, 3, 1. So here we get x cubed 3 x squared delta x plus 3x delta x squared plus delta x cubed. Now the expansion, when we go x plus delta x to the nth power, you can kind of see what's happening here. The coefficients go using Pascal's triangle, and the x powers go down by 1 each time, and then the delta x powers go up by 1 each time. And so this is what that looks like mathematically. So we'd get x to the nth plus n x to the n minus 1 delta x plus, now here's the tricky one, n times n minus 1 times x to the n minus 2 over 2. So this here is that formula which will give us Pascal's triangle. And this is going to be multiplied by delta x squared plus. And we're going to keep continuing in this pattern. So we're going to just do dot, dot, dot. And finally, at the end, we're going to have delta x to the nth power. Okay? So don't worry too much about how we came up with this, but we are going to use it now to find the derivative of x to the nth power using the limit definition. So let's go ahead and write out the limit definition here. So remember, it's f of x plus delta x. So we're going to substitute x plus delta x right in here. So it's going to be x plus delta x to the nth power, and then minus f of x, which is just x to the nth. And this is all over delta x. All right, now we've already done this expansion up here, so we're just going to rewrite this entire thing for x plus delta x to the nth power. So we have the limit delta x goes to 0. We have x to the nth plus n x to the n minus 1 delta x plus n times n minus 1 x to the n minus 2 over 2 delta x squared. And that continues on until we get to delta x to the nth power. And don't forget, we still have this minus f of x, so minus x to the nth. And this is all over delta x. Now, if you remember doing the limit definition with actual functions and numbers, you found that lots of things canceled out. And so we can see here this x to the nth and this minus x to the nth are always going to cancel out. It doesn't matter what n is. Okay. Now, when you look at this, we can also see that every term is now left with some sort of delta x. So we have our delta x down here. This term has delta x in it. This term has delta x. And it turns out every term has delta x. Well, we know if we're going to take a delta x out of each one of these, right, it's going to just cross out here. What happens to the power if we do delta x squared over delta x? Well, that's going to go down by 1, right? So that's just going to be to the first. And so if we have delta x to the nth power, that is going to go down to n minus 1 because we're taking a delta x out of it. Okay, now, after all the smoke clears, remember our goal is to let delta x go to 0. So any delta x's that are remaining are going to change into zeros. So this one is going to change to a 0, and this one's going to change to a 0. Notice this one already got canceled out. So if all this stuff is multiplied by 0, it's really gone. And this, if it turns into 0, is also gone. So when all the smoke clears, what we're going to be left with here, what's the only thing left? Looks like it's going to be right here. Okay? And so overall we get n times x to the n minus 1. So a lot of complicated stuff happening. And you can remember the pain it was to do the limit definition. And after all that, we're left with something this simple. And that is the beauty of math and the beauty of calculus. So if n is a rational number, then the derivative with respect to x of x to the nth power is n times x to the n minus 1. Okay, so just looking at, if we're taking the derivative here, the n is going to come in front, and then we're going to subtract 1 right up here. So that's your process on how to do this. All right, let's try a few examples. So if we think about our first function, it's just x. And when we do this, this is really x to the first power. So if we're going to find our derivative, that 1 is going to come in front and multiply the x. And then we're going to have 1 minus 1 on the top. Well, we know this is x to the 0. And so we know this equals 1. Now if we think just for a second that the derivative is the same thing as slope, what's the slope of this function? Well, we know it would be 1. And so here we can see that the power rule works for linear functions. Let's try the next one together. Here we have x cubed. So we're going to apply our power rule now. So the 3 is going to come out in front and multiply the x. And then the 3 is going to decrease by 1. And we get 3x squared. For our radicals here, it's always good. Notice the form is x to the nth power. So we want to write it as x to the nth power. So this is really x to the 1/3. So remember we have the 1 here and the 3 here, so 1/3. So let's go and find g prime of x, our derivative. So the 1/3 is going to come out in front. And then we're going to subtract 1 from 1/3. So remember, this would be 3/3. So 1/3 minus 3/3 is negative 2/3. So here we have 1/3 x to the negative 2/3. Now with negative exponents, we don't want to leave them negative, and we actually flip them under the fraction sign. So this one would become 1/3x to the 2/3. And there we go. Now in calculus, we don't worry about rationalizing the denominator. We can leave radicals down there. All right, for letter D, here we have 1/x squared. Again, we want to get this in the form x to the nth power. So this really becomes x to the negative 2. So we just flip it into the numerator and then change the exponent to negative. And so y prime here is going to be negative 2 times x. Now be careful here. This is negative 2 minus 1. So this really becomes negative 3. So our answer here is negative 2x to the negative 3, which then we can flip the x under into the denominator and becomes positive 3. So it's negative 2 over x to the positive 3. All right, so getting the hang of it. So change it so that it looks like x to the nth, and then just multiply by the n, go n minus 1, and then clean up any loose ends at the end. Now, we're going to use the power rule here to answer this question. It says find the slope of the graph of f of x equals x to the 4th and the equation of the tangent line at that point when x equals negative 1. So we're trying to find right here what is the slope of the graph at this point. Well, before we do anything here, we know the slope of a graph is the same as its derivative. So we're going to go ahead and find f prime of x. Okay, and using our power rule, we can do 4x cubed. Okay, so that is the function for the derivative. So looking at this right here, the slope of our function is going to be 4 times -1 cubed, which is just -4. Now, they also want us to find the equation of the tangent line at the point. So at -1, we actually need to find another point. So this is the point -1, comma. Okay, we're going to plug -1 into our x to the 4th, and that becomes 1. So now we have a point and a slope. We can find the equation using the point-slope form. So y minus y1 equals mx, or m times x minus x1. So we can see the double negative would become positive. And our final equation here would be -4x. And then we add the 1 to the other side. -4 times 1 is -4. So we get -4x minus 3. So from that, we could make our tangent line right here. All right, I want you to go ahead and try B and C on your own. Again, it's just plugging the x into our derivative function and then finding the equation using a point and the slope. Go ahead and check your work here, and then when you're good, let's move on. Next, we want to talk about the constant multiple rule. And again, we're going to use the limit definition to help us find what happens when we take the derivative of a function that's being multiplied by a constant c out in front. All right, so we're going to take the limit as delta x goes to 0. And we're going to use our difference quotient here. And so now we're going to have c times f of x plus delta x minus c times f of x all over delta x. Now here we could factor the c out of the numerator. And from our properties of limits, we know that c then can go on the outside of the limit. Now what we're left with here is just the difference quotient. So the limit as delta x goes to 0 of the difference quotient, that is the definition of the derivative. And so what we're really left with here is c times f prime of x. So that tells us then that this equals this. So if f is differentiable and c is a real number, then the derivative of the constant times the function is just constant times the derivative of the function. So what that is telling me is that constants can be factored out of the differentiation process, even if they appear in the denominator. So it doesn't matter where they are, you can just factor them out to the front and then take the derivative. So let's try some examples here. Now first, if we have 2 over x, we want to go 2x to the negative 1. So we do still want to get that form x to the nth power, or c x to the nth. So now what this is telling me is that if we take the derivative of 2x to the negative 1, we can factor out that constant 2, and then simply what we can do is factor out that constant 2 and then take the derivative of x to the negative 1. So we get 2, and then we're going to apply the power rule here. So negative 1x to the, well, negative 1 minus 1 is negative 2. And then we just have to clean this up. So 2 times negative 1 is negative 2, and then x to the negative 2 becomes x squared in the denominator. So this is kind of the roundabout way of doing this. What we can do is we can combine the power and the constant rules to form one rule here. So if we have the derivative of c x to the n, what we can really write is the derivative equals c times n x to the n minus 1. And we can end up doing this all at once. Okay, so let's try that here with letter B. So here we have 4/5 t squared. So the 2 is going to multiply the 4/5. So it's going to be 4 times 2 over 5. And then t squared is going to become 2 minus 1 is 1. And then all we have to do is simplify. So we have 8t over 5. For letter C, we don't like radicals, so we do want to deal with just fractional exponents. So this is 2 times x to the 1/2. So y prime is going to be 1/2 times 2. And then x to the, let's see, 1/2 minus 1 is negative 1/2. Now if we clean this up, 2 times 1/2 is gone. X to the negative 1/2 is going to go in the denominator, and we'll just write it as the square root of x. Okay. Let's try our next one here. So when we look at this, we do want to rewrite it. So let's get rid of our radical signs. So this becomes 2x to the 2/3. Now we're going to change the 2/3 into negative. So we have 1/2 x to the negative 2/3. And now we're going to go in and find our derivative. Okay, so we're going to go negative 2/3 times 1/2 x to the, let's see, well, we want negative 2/3 minus 1. And instead of writing minus 1, let's write minus 3/3. And so let's do some of this here. So negative 2/3 times 1/2 is going to be, let's see, the 2's are going to cancel, so we're left with negative 1/3. And then negative 2/3 minus 3/3 is negative 5/3, so x to the negative 5/3. And then we don't want the negative exponent, so we're going to have negative 1 over 3x to the 5/3. And we will leave it just like this. All right. I want you to try letter E on your own. Pause the video and come back when you're done. I should have gotten -3/2 here. So it's just the slope -3/2 right in front. Now for letter F, when you see this 2x is in parentheses cubed. So that is different than this cx to the nth. So when you have something in parentheses cubed, you always want to go ahead and cube that. So you get 2 cubed is 8, and x cubed is x cubed. So get it into this form, and then you can find the derivative. Now I do want to show you another shortcut, and it's the reciprocal power rule. So instead of flipping this up as x to the -3rd and then doing all of that, we can say, well, if we have c over x to the nth power, we can think of this, right? We would flip this up and it would become x to the -n, like this. And then if we did this, we would get -n cx to the -n minus 1. Then this would go ahead and flip all back under. So really what we're having here is we can go -n times c to the x to the, well, if we take a negative and we subtract 1, that's like taking n and adding 1 in the denominator. So it's a nifty little trick. Let's try it here. So here n is 3, so we're going to do -3 times, we'll leave our constant in there, and then we want to add 1 right here to the 4th. So this becomes -15 over 8x to the 4th. Pretty slick, huh? All right, let's move on. Now the sum and different rules, we're not going to show you how the limit definition works for these. We're just going to go ahead and define the rules. So if we have the derivative of one function plus another function, and they're added together, this is like taking the derivative of the first function and adding it to the derivative of the second function. So you can do the derivatives separately and then add them together. The same thing works for the difference. So if we have the derivative of a function minus another function, so it's really the derivative of the first function minus the derivative of the second. So just as you would expect it. Now what this allows us to do is find the derivatives of polynomials. So we really have 3 functions happening here. Okay. So f prime of x here is going to be the derivative of x cubed, which is 3x squared, and then the derivative of 4x, which is -4, and then plus the derivative of 5, which is 0. So we do get 3x squared minus 4. Okay. I want you to try letter B on your own. Pause the video and you can come back and check your work. All right, welcome back. You can check your work right here. Hopefully you're getting the hang of using the power rule. Let's move on. The next thing we want to talk about is the derivatives of sine and cosine functions. So here you see I've given you the graphs of each one here. So here's our cosine function, here's our sine, and we can see here that the relationship between the derivatives of one and the other are kind of related. So if we look at the derivative of cosine at 0, okay, what is that slope? Well, the slope is 0. And if we look at the sine function equals 0 at that point. Okay. Now if we keep going down, the slope right here actually is -1. And what's the height of the sine function here? The height is 1. Okay. Again, we can think, well, what's the slope of the sine function right here? Well, the slope of the sine function is 0, and then the height of the cosine function is 0. So there's some sort of relationship here. Now here, if we look at the sine function, the slope is going to be -1, and then the height of the cosine function is -1. Okay, so the slope is -1, here our height was -1. Here the slope is 0, here the height was 0. Here the slope was 0, the height was 0. What's the slope of this function? That looks like it's +1, and then the cosine is 1. So the way this works is the derivative of the sine function is the height of the cosine function. And the derivative of the cosine function is the opposite of the sine function. And you can spend a little more time if you want to try to see how that works right over here. But you can also memorize these. Derivative of sine is cosine. Derivative of cosine is negative sine. So you will have to have those memorized. So let's go ahead and find the derivatives here. We have y equals 2 sine x. Okay. We know the constant is going to mean that this just stays as 2. And then the derivative of sine is cosine. So we get 2 cosine x. In letter B, try this one on your own. All right, you should have gotten cosine x over 2. And letter C, here, y prime. Well, the derivative of x is just 1, so this is that sum of derivatives here. And then the derivative of cosine x is, well, minus sine x. All right, so that is derivatives of sine and cosine function. Pretty simple. You just have to remember which one change a sign and which one doesn't. All right, our last topic for today is derivatives and rates of change. And the derivative can be used to determine the rate of change of one variable with respect to another. And it's actually what the derivative is. Now, if we recall, distance equals rate times time. The derivative is a rate, so we'll solve for rate here. So rate equals distance divided by time. Okay. Now, we can find the average rate of change. And this is something you've already done before. And we just let s of t be a position function of an object. So this is its position. And the average rate of change is going to be the change in its position over the change in time. And this is going to be the average velocity over that time period. All right, so an example. If a billiard ball is dropped from a height of 100 feet, its height in feet s at time in seconds t is given by the position function s of t equals -16t squared plus 100. So this tells us how high the billiard ball is at a specific time t. Now we want to find the average velocity over each of the following time intervals. So this goes from time equals 1 second to time equals 2 seconds. So an entire second elapses. We want to know what was the average speed over that time. So what we have to do here is find the position at time equals 1 and the position at time equals 2. So we're just going to plug 1 into our function for position. So we have -16 times 1 squared plus 100. And this equals 84. And then we have -16 times 2 squared plus 100. And this equals 36. So now we're going to use our average rate of change right up here, delta s, so the change in s, over delta t, the change in time. So delta s is going to be 36 minus 84. And so we're going to take the first one and put it second, and the second one and put it first here. Okay, and then the change in time, it goes from 2 seconds to 1 second. Okay, and again, it doesn't matter, I guess, which one you pick first, as long as you are consistent with which one you pick first. And this gives me negative 48 over 1, and this is going to be feet per second. Now, why is the velocity negative? Well, because the ball is dropping, so that's why we have a negative velocity there. So that's the average speed over that 1 second. Now what we're going to do is cut that time by half a second. So 1 to 1.5, and we want to find the average velocity there. So again, we need s of 1, which we already know is 84. And we want to find s of 1.5. So we're going to go negative 16 times 1.5 squared plus 100. And this gives me 64. So again, we're going to do delta s over delta t. So we have 64 minus 84 over 1.5 minus 1. And we get negative 20 over 0.5. And if we divide something in half, it's like multiplying it by 2. So this is negative 40 feet per second. I want you to go ahead and try C on your own. So find the average velocity in that 1/10 of a second, 1 to 1.1. Go ahead and pause the video and come back to check your work. All right, welcome back. You can go ahead and check your work here. You should have got negative 33.6 feet per second. Now, hopefully you can see what's going on here. We have 2 seconds, 1.5 seconds, 1.1 seconds. What we're trying to do is let that delta t disappear. Now, if we let delta t go down to 0, we're going to actually find the actual rate of change, or actual velocity, at time equals 1. And it turns out, by letting this go to 0, all we need to do is find the derivative of our position function. So we would want to find s prime of t, which is negative 32t to the first power. So the instantaneous rate of change here is just going to be negative 32 times 1, which is negative 32 feet per second. And you can see here our limit as delta t went to 0 is getting closer, and it would have been negative 32 feet per second. So let's just say that s of t is a position function of an object. The instantaneous rate of change, or the velocity, is the derivative of the position function. So our function v of t is s prime of t. So an example, at time t equals 0, a diver jumps from a platform that is 32 feet above the water. The position of the diver after t seconds is given by negative 16t squared plus 16t plus 32. The first question, how long after the diver jumps will the diver hit the water? So if we think about this, here's all the water down here. You got your little diver. And this is your position, s of t. So if he jumps off and he hits the water right here, what is the position? Well, the position is 0. So we want to know where 0 equals negative 16t squared plus 16t plus 32. And this is algebra 2, just solving for a polynomial, for a quadratic. Looks like we can factor out a 16, a negative 16, so we have t squared minus t minus 2. And the negative 16 won't factor into our answer. Now we want to factor t squared minus t minus 2. So we have t minus 2, t plus 2. And this would give me the solutions t equals 2 or t equals negative 2. And we don't deal in negative time, So at time equals 2, okay, so it takes him 2 seconds to get down to the bottom. So what is the diver's velocity at impact? So we have to remember that the velocity at time t is the same as the derivative of the position at time t. So let's go ahead and find the derivative of this right up here. So we have 2 times negative 16, which is negative 32, and then t to the first, so t, and then here would be plus 16, and then plus 0. So all we're going to have to do is plug 2 into this equation. So we want s prime of 2, and that equals negative 32 times 2 plus 16, giving us negative 48 feet per second. So that is how we can apply this idea of derivative to some real-world examples. All right, I hope you feel comfortable with these rules, and thanks again for watching. We'll see you in class.